So welcome back, guys. So this week, as you all know, you have your midterm coming up. So we're gonna just jump right into it, and I'll be going over the practice midterm. I know some people have reached out asking about whether like the answer solution to the midterm. So I figured I would work through some of those and just see if there's first of all if there's any questions, and then we'll work through some of the problems to make sure everyone's on the same page, and then go from there if that works. Some of the ones on the practice midterm were a little bit trickier than I anticipated even myself. So like if there's any, we'll work through those and basically get to the solution through an actual interactive tutorial. So if that works for you guys, that's what we're going to be doing today. So yeah, did anyone, first of all, have any questions or any, like you want to start with a certain question for the practice midterm or? No, I'll just jump in. Sorry, go ahead.
So I did 6.
Okay.
That's an example when we talked about class.
Yes.
But for 6.
Sorry, 6. This one. This one.
So yeah, you did that one in class. And so I know the answer, but I wasn't sure I guess this is how to explain it. It just comes down to like here it just says the face cake back. But I'm still kind of shaky on it, like with the Deutsch algorithm.
Right.
Looking at it in the sense of like, what do you call it, coherence.
Right.
It kind of makes sense. But with this one, I couldn't really, like, coherence doesn't seem to make sense of why, because there's no measurement on the other bit. And even if you measure the other bit, it's kind of confusing how that would affect the first one, because the measured one and the other bit, I get the measured bit to be 1 on the bottom.
Mm-hmm.
So I'm confused why that would be that top one has to be 1 as well.
So did you actually? So the question is, yeah, I'm assuming you've worked out the question and you've seen like what the result is on each of the bits, but still, I was confused like the intuition as to why.
Yeah, more just like so. Yeah, I could explain that. Okay, yeah, there is a difference, but I don't know how to explain why the difference is there.
Right.
Other than just saying face cake.
I mean, I think that. At least as far as I understand, the only explanation you need to say the why is really phase kickback. At least that's the conclusion I reached. Yeah, because I don't think there's any more to like understanding between the coupling of the math, as far as I'm aware, the intuition between like, this is like, you could say like from a math perspective, this makes sense, and this phenomenon, we call it phase kickback of this coupling, but yeah, I don't know, I couldn't explain personally any more of what you have to like the why. And even in the question, he just says whether to refute or to confirm the classical intuition, so it's not really even explained. But yeah, I do agree with you. Like, I would like a little bit more as to like what is actually physically going on here. But I personally cannot get to that, and I don't think I'm not sure whether we'll actually go more into that in class or not. So
Yeah, I might ask in class just to see if it's something we're expected.
Yeah, I don't think the why is always tricky, obviously, because we're in quantum mechanics, so like having an intuition of it is always just like, you can't really have as much of an intuition. We try with analogies and stuff like that as much as possible, but at some point it's just like, the math works out that way, so this is how it is. But yeah, great question though. I would also like to know if there is a better why, so that's a good question for him in class. Mina, any questions about, do you practice midterm? Do you want me to work through the questions, or from you, did you work on the practice midterm? Or?
I haven't gotten a chance to work on it.
No worries. So we can just go through in order then, and I'll start working through some of them if that works for you guys. And we'll start with one, start off easy, and then go from there. Okay. So yeah, if you look at the practice midterm, most of them are pretty straightforward, and he gives pretty much all the definitions on here. So I'm anticipating and expecting, he hasn't given me the midterm personally, but I'm anticipating that it will be the same way, where he'll give you basically the definitions of everything, and then we'll get to work with it and work through all the questions. So this first one, we start off, it's a little bit of adds a little bit more terminology here than maybe we need to, but it's just the basic formula that we've seen before in class. I'm going to split the screen here just to open up my notebook. So let's see if we can make this actually look nice. So this first definition here is he's basically giving you the definition for a unitary function gate. So we don't generally present it this way in class. In the actual class, we'll do u underscore f is equal to like x, unit square x of x or y is equal to x and then y XOR, I'm going to just call it XOR because I don't know how to actually put it, but this is the general formula. It's the exact same thing as this one here, but it's just stating on my left-hand screen that there can be more parameters in this actual equation than before. So, for example, if you have, say, instead of n b of n's, you only had 3 b of n's, or like 3 inputs to the equation. Let's do an example. Let's do u of f of something that had 3 parameters, and I'm going to call them w, x, y, and z. So that's our 3 inputs to our theoretical unitary function. These first 3 right here are considered the b of n on this equation here, and this last one, h, the last parameter, is going to be our parameter z for that equation. So hopefully that makes sense, the way the equation, the way it's written here, kind of like the math, you got to put one to one together, but if you get through that part, you can just see that on the right-hand side of the equal sign, we'll have w, x, y, which are bn's, and then our last one, which is f of w, x, and y, which is our equation, and that's XORed with z, which is our h in that equation. So hopefully that, at least, like, you can follow that. So it's just basically adding a longer version of the equation that we've seen in class, so that we can see it or work with it within any different function that has more than one parameter. So the first part of this question then, first of all, any questions on that? Does that hopefully make sense for you guys? Okay, great. So then the first part, the question 1a, which we'll get to, is what is the value of a u-naught function? So I'll call it u underscore naught on the right-hand side. So it wants what this expression is u-naught of false, false. So in the explanation above, it gives us a couple different functions that we can work with. And so it says not is just Boolean negation, so we can assume that that would just be the not of any of the arguments given inside of it. So in this example, we're going to call it f of x is equal to x. I'll say not of x, because I don't know how to put the line above it, but f of x is equal to not x, essentially. So that's our function that we're working with, or I'll call this f underscore not is equal to, you just not it. So now when we put that into the Boolean function, or sorry, into the unitary matrix itself, let's figure out what u naught is. So u naught is equal to, so we only have 2 parameters going in there, so we're going to have an x and a y, and that is going to be equal to x, and then y, x, oh sorry, I should do it the other way around, f of x XOR y, and there should be spaces there if this was an actual programming language, but I'm just writing in text. And in this case, f of x is our f naught of x, so we're gonna place that with f naught of x, which is just naught of x. So skipping a couple steps, it basically would just be naught of x XOR y. So that we can then plug in our actual 2 inputs, which are false and false. So we can do u underscore naught of I'm gonna put true and false as f and t. So I'll make a note of that up here just for the actual working through. So true equals to t, and then false equals to f, just to make it a little bit easier to write. So then if we put that into our actual equation here, it should be x of not of false XOR false. So if anyone remember off the top of their head what an XOR, what the truth table for an XOR is, given an x and a y? It's a little bit, the word exclusive OR is always kind of the one that I like to remember. It's like XOR is if you have an odd number of ones, it'll come to 1.
0, 1, 1, 0.
Yeah. 0, 0, 1, 0. And the next line, 0, 1,
1,
1. And then 1, 0 comes to,
1,
and then 1, 1 is
0.
perfect. All right, thank you guys. So yeah, since that is the XOR of it, since we have not f, which is true, that is true, and then it's going to be true or false, which is then just true. So then that expression evaluates to x or true, or sorry, false or true, because x is false. So that is our answer there. So I'm not sure actually in the question whether he's actually looking for the full value of the matrix or just what the output expression is, assuming like this is our last one, but if you really wanted to, we could call it, say, the output. The output is true. And that's at least how I'd work through that question. So let's go on to B. I know it's pretty much the same form. If you guys want, I can move on from this question or work through some of this couple of these are a little slightly different. But if not, I can just keep working on some of these to see how they work. But if not, I'll move on to the next question. So would you rather I keep doing some of these or move on to the next one, or let Chris or anyone decide? If you get this one, it's pretty straightforward for the rest of them.
Yeah,
But
if Chris doesn't have any particular questions, I think we can go to the next.
okay,
I think the rest.
okay, perfect. Yeah, this one is pretty straightforward. Of course, if anyone has any particular questions on any of these, like feel free to reach out to me. But the actual formula is pretty straightforward. Yeah, let's move on to the second one. I'll make this slightly bigger on the screen.
There's going to be solutions for the
Like official solution. Like I don't think he's getting a solution. If you want, I can release solutions. If that is, you find that would be actually helpful. Like I can, like you, would you prefer fully worked out solutions or would you prefer just the answer key?
Either's fine. I just would like to at least check.
Okay, sure. Yeah, I will. I can get that. I can do like I can ask Dr. Sabri. I'll show him my answer key and then like see if the answer key works for you guys, or I'll double check with him if that's the right answer, and then get his.
Like, I would want it to see, like, the format that he's expecting for all of the answers.
Okay. Yeah, I mean, when I'm marking, I don't think I will be doing formatting. I will be doing content and like making sure that the right answer, and then if not, trying working through the way that you like see the way you guys have written it. So that's the way I'll be marking it. But if you prefer, like I can see if my format lines up with his. That makes you more like comfortable for the midterm. Yeah, absolutely.
I mean, like, if you're marking, then however you end up doing it is perfect.
Okay. Yeah. No, totally fair. Yeah, I won't be like, oh, you didn't do it like the way I would have done it. Like, wrong, totally wrong. I'll try and actually work through and follow your logic. So I guess the biggest thing I think for me then for the midterm to help me mark it is just try and explain yourself. Don't just be like write cryptic messages and then be like, okay, maybe it's this, because then if it's not right, I won't be able to follow the logic. So obviously you don't need to write paragraphs and paragraphs, but like a little bit of like documentation and comments, essentially just comments if we were writing code, but in a midterm format just to like help me follow your logic when I'm marking and stuff like that. So that is the best suggestion. But yeah, I'll talk to Dr. Sabri about actually getting the answer key to this practice midterm just to help solidify it. And then, yeah, we can go from there. Okay, good question though, because yeah, if you guys feel more comfortable, I know for midterms it's always like, it's very stressful, so I also do want like explicit solutions to everything like that. So I'll work on that. All right, second question. This one is a little bit of mix of Qiskit and a little bit of quantum mechanics and a little bit of logic tables. So this one gives us essentially a circuit and says that we need to write down an equivalent circuit that just uses one of these circuits. So yeah, given we can draw out this circuit, and at least that's the way I would go about it, is drawing out the circuit, going through the truth table, and then actually seeing if there's any equivalent, like single gate that will lead to that truth table. Does anyone have any alternate ways that they would go about it? Like, I don't know, Chris, did you go about it a different way when you were solving it, or?
I did the same thing.
Okay.
I had a little trouble going from the truth table to figuring out what the gate would be.
Yeah.
I think he did an example in class like this.
Oh, did he? Okay.
They used the, like, I don't know, the broadcast notation. But he like writes it all in broadcast notation, and then you get a final, like after applying the gates, you get like a final expression.
Right. Okay.
It's another way that I thought to do, just because after I got the truth table, I wasn't sure what it was. So.
Right. Yeah, that's totally fair. Yeah, sometimes it's a little bit tricky just to like work from the truth table. This question, I'll work from the truth table, and there's another question where we do it with the superposition, so maybe I'll do the broadcast notation for that one, and then go from there. So yeah, this one will do the truth table. It's a little bit tricky because sometimes it's one of those things is like you have to see it to see it. So just doing the practice yourself actually just helps to like be like, okay, like maybe I can. But the goal, like the fun, sorry, I'll actually do the question, but the hint here is that we only are going to be using one gate at the end. So no matter what, if you write down all the truth tables for all the gates that we know so far, I mean, we're only going to be using NOT, CX, CCX, or maybe Hadamard, but I'm assuming it's not in the superposition, so we can assume it's not any of the like quantum ones. Write down the truth tables for those, compare it, and see like, okay, what can I do to get these inputs and these outputs? So that's my like tip if you're like, because it's hard to see. But yeah, let's actually work through it, and we'll go through it and see what the actual output is. So question 2. So we're going to be basically doing. I will actually write out the circuit diagram here, or sorry, we'll draw out the circuits of what it should actually look like, and we'll go from there. Okay, so let's copy this in here. And then we will actually do the lines. Sorry, I'm using the OneNote, so it's kind of a little bit messy, but hopefully you should get the idea. So I'm going to call this Q0, like that, Q1, and then Q2. So these are my lines. I will draw them out as best I can. There's one that's pretty straight. That's pretty straight. Pretty straight. So our first one is CCX, Q0, Q1, and Q2. So that means the last one is always going to be our NOT gate, if you remember from Random Qiskit. So we're going to have a loop. Oh, let me draw. Loop. So the NOT, or the end of Q0 and Q1 will NOT this last one. That's a bad NOT, but it'll work. Second line, NOT of Q0, so we're just going to add a plus here. Bad plus, bad drawing, but you get the idea. The last one is just doing the same thing over and over again. So repeat that. Loop, loop, plus, hopefully, and then same thing over here. So this is our circuit diagram. So yeah, my suggested way is to go and make a truth table for this circuit, and then try to see an equivalent truth table only using one gate. So that's the method we'll try to go through. So we're going to make a quick truth table for inputs, all the different inputs, and we'll go from there. So we'll do Q0, Q1, and then Q2. And then I'm going to call them prime over here for what the actual output is. So I'll call them Q0 prime, then Q2 or Q1 prime and Q2 prime. Q1 prime, and Q2 prime, Q2 prime. All right. Q0 prime, Q0 prime, Q1 prime, and Q2 prime. So yeah. That's at least the way I like to put my truth tables, but obviously you don't need to copy it. You can call the outputs whatever you want, as long as I know, at least when I'm following along, what the inputs are. So I'm just going to count binary up on the left-hand side for our inputs. Oh, that's not going to work. Then 0, 0, 1. Nope, sorry. 0, 1, 0. I really should be doing this in Excel, but I'm sure it'll be fine. 1, 0. On going 1, 0, 0, and then 1, 0, 1, and then 1, 1, 0, and then 1, 1, 1. So there should be 8 inputs on the left-hand side because it's 2 to the amount of inputs, or sorry, well, 2 to the x, where we're x, we have 3 inputs, so 8 different possibilities. 1, 2, 5, 6, 7, 8. Great. So a quick thing for doing the truth table, because you might think, yeah, there's a lot of different possibilities that I want to work through. Is to notice on the actual circuit itself that because it's a classical circuit, we don't have any superposition or anything going on like that. The first line, no matter what the input is, the output should always be the same because we're just nodding it twice. So, Q0 nodded, doesn't make anything. There's no phase kickback. So we can actually just copy our Q0 here into our Q1. Oh, that's not how you do it. Hopefully, please let me do it. Oh, it's embedding in there. But we can copy our Q1 because it's all going to be the same. There's nothing fancy, no superpositions going on. And then our Q1 will also be the same input and output, so we can copy that going forward. 0, 0, 1, 1, 0, 0, 1, 1. And so the only thing we need to figure out then is all the outputs for our last part of our Q gate, or Q2 prime, which is actually where all the action is happening. So basically, you're just going to run through all the different inputs and see what the different outputs are. So 0, 0, there should be no outputs. It's just getting, there's no knots, no anything, so it should be 0. The next one, 001, there's also no knots, no C naught action happening. That's just a 1. The next one, 0100. Oh, right, sorry, the first thing, yeah, remember that they're both being knotted before getting to the second C naught gate. So you got to make sure that the actual input is 1 up here. So if the second gate ever becomes 1, or the Q1 ever becomes 1, then you need to flip it. So this is our first case here at the input 0, 1 for Q0 and Q1, where, and I'll underline it just to show that it's being flipped, where it goes flip from 0 to 1. Because at this point we have I'll draw it in red, we'll have a 0 here, and then a 1 here, and then a 1 here, and then a 1 here. So that activates the second C naught gate, and that's why that gets flipped. So then on this next, everyone follow with that. Hopefully makes sense. We're just going through different possibilities of what it will actually be at that gate there. So then on the next line will be the same thing, because we're also going to have the input 0, 1, which is going to turn into a 1, 1. So that means we're going to flip our last qubit, or Q2 will then become just a 0 here. So I'll also underline it again to be that. So that means we have 2 situations where the actual second C naught gate has been activated. Going on to the next one, so now, because this one is going to become a 0 after we knot it, so I'm going to erase this, and we're going to look through it and say that it's become a 0 now after this gate. And then this line is now actually a 0, so it's going to stay 0. So for these 2 inputs, 0, 1, 0, and 1, 0, nothing's going to change. It's just going to output 0, 1, and 0, 1. So we're going to go through 0 and 1. And then the last line is where it's the most fun, because what it starts out as is there's a 1, 1. So I'll actually draw this on my circuit diagram in bad drawing. Oh, please erase. No, there we go. That's not what you want. Oh, I see. Sorry, I couldn't see where the actual erase head was. So yeah, so now it starts off, there's a 1, 1 here. So it's going to knot our input. So our input going from, whatever we want it to be, say X to X naught. After that, I'll draw a bar over it to designate a knot. Hopefully you can see that on the actual screen. I actually didn't think to look back there. But after this knot, though, it becomes a 0 and a 1. So nothing happens there. So then only this first CX gate is applied. And then, so the output here, again, will be flipped for these 2 scenarios, if that makes sense. So here, it's going to be a knot again. So it's going to go from 0 to 1. And it's going to go from a 1 to 0 in this case and be flipped again right here. So everyone hopefully follows that. We're just basically going through all the different, generating the truth table for this circuit. And then the trick part is how do we generate an equivalent circuit that is made up of this using only 1 gate. I could just give it away, but maybe we should try do you guys want me to do out the truth table for the other, X, CX, and CCX and see if we can see it? Or does anyone see it right away? I'm assuming no one sees it right away.
I think you can tell because it only depends on the middle bit.
This one right here?
On Q1.
Q1,
Q2
right.
is only flipped based off of Q1.
Yeah.
Because for Q0, it's going to be, even if it's 0, it'll get flipped at one point. And then if it's 1, it'll just go through for the first, CCX gate. So it just depends on Q2, Q1.
Yeah, absolutely. Yeah, that is absolutely it. So yeah, great noticing. You're you kind of really just got to pick it up. Like you said, for these 2 gates, sorry, where's the actual highlight? As long as there is, only when this turns 1 will this actual bits get flipped here. So what kind of gate would we want to make that would do it in this case scenario then?
You could do CX with Q1 and Q2.
Absolutely, got it. That is the thing. If you do see it like that, perfect. That's the way to do it. But if not, the other way is just to go through and generate the truth table, equivalent circuits for all the other ones, giving a sorry, what am I trying to say here? Generate truth table and see where you can see those same patterns and similarities. But you absolutely are correct. It is just a single NOT gate between those 2.
So then if you were marking a question like this, you'd want to see the truth table, right?
You don't have to show the truth table if you know, it is correct if by some chance you see this question and go, oh, that just like works by Anaki. If you give the answer, like you got the answer. I don't know how. I'm not going to assume that you're cheating or anything like that. You got it. Showing your work obviously is best in case you don't get it right. So show as much work or use as many words as you feel are adequate to explain it. But I won't be like, unless in the question it asks for the truth table, they don't need to show the truth table. This is just the way I'm actually going through it. But yeah, good question though. It's like, what am I expecting to see? As much as you reason, it's not a good answer, but as much as you reasonably think needs to be explained for the question. But yeah, unless it's asked in the question, I won't be marking it wrong if I don't see a truth table or anything like that. So, all right, so let's. Oh, that's not going to be the lines, but let's just draw them in here. But yeah, exactly like I said, Yamina. The equivalent circuit is just a CX between this and the second line. So we could just write that an equivalent circuit would be CX between Q1 and Q2. Yeah, it probably wants it to write us in Qiskit notation. So yeah, that's exactly what we did. CX1 and 2. So yeah, that is question number 2 all done. Any next question you want me to work on, or just move on to the next one? This one right here. This one is basically kind of the exact same, but now with superposition involved.
You mentioned we could try this using like the bracket notation.
Yes. So this one, I will do that in bracket notation. We'll go over there. Yeah, absolutely. It's going to be a little bit messy to do in OneNote, but hopefully you guys can follow along and we can get this through. So I will actually consult my notes as well, just to make sure I don't mess this up. So. This one is now, so it says that we're introducing a new gate called the Zed Gate that's defined as the following, as seen in the PDF. So if we have 0 as our input to the Zed Gate, then our output's going to be 0. And if we see a 1, we're going to like add that little negative, like I think it's called the negative phase to it, and it's going to called like now it's going to go from 1 to -1 essentially. So it's kind of like a controlled version of the like CX gate, but now we're dealing with superpositions here, and you won't see that right away, but just I'm letting you know that. So it's only going to flip and do this case scenario when the control bit is true. Sorry, actually, let me actually show the actual slide sheet. So the CX gate will only change a 0 to a 0 and a 1 to a -1 when the control bit is true. So it's not nodding the gate, it is like doing this action to the gate when the control line is 0. So I'll draw an example of what that actually looks like, just to make it more clear. But essentially, we are just having this gate and now trying to work with it. So then now we have a new circuit fragment using this gate, using the notation, where we're going to have a Hadamard on Q1, a CZ on between Q0 and Q1, and then another Hadamard. So, and then now we're doing the exact same thing as the last question, where we have to do an equivalent circuit fragment using all of this. So, any questions on the setup on the question? Hopefully that makes sense. Okay, good. And then yeah, so now let's try it. Yeah, the way you can't really, well, you can sort of use a truth table, but like let's do it actually using the proper bracket notation so that we actually go through the circuit properly. But let me just draw the circuit first, and well, let's first draw the CX gate just to make sure it's extremely clear for everyone. So we'll call this question 3. We'll underline that. So the CX gate is going to look something a little like this if we had an actual gate. And I'll actually mark this and say it's the CZ gate. I'm saying CX because I'm thinking of not, but it's the CZ gate. And then for a given Q0, or sorry, that should be 0, or Q1, if we have a CX gates between here and here, so I'm doing notation where it is 2 loops to make a CX gate. I don't know if that's just the way that Qiskit Composer puts it, and I'm not sure if that's actually how you represent a CX gate, but I'm just doing 2 loops. It's hard to tell which one's the controlled one and which one's the not, so that's why we have to actually use like this notation to see like which one is the controlled, one's the not. But in this case, the one that's being actually, like this is the control, I'm going to mark it with a C here, and then this one's the actual thing that Z is being applied to, if you follow what I'm saying. So it's always going to be the second one that is having the Z actually applied to it. I'll underline that. So Z is being applied to Q1 whenever Q0 is 1. So if Q0 is normal, actually we can even do a truth table here for CZ. Truth table. So let's do Q0, Q1, and then Q0 prime, and then Q1 prime. And sorry, yeah, I'll just say like, hopefully you can tell the output of like where Q01, Q0 prime are at the end. So Q0 prime over here, and then Q1 is over here. Q1. So yeah, sorry, I know I said I wouldn't be doing any truth tables, but I just like it for just to explain how the QZ gate actually works. Hopefully that is okay. And now I'm going to use it actual inputs for broadcat notation. Just now because we're actually dealing with superpositions essentially. So the Q0 bit is never going to change no matter what the input is. And since the actual control bit here is 0, the output is also going to always be a 0. Then same thing for if we're to count in binary, if Q1 or output is 1, the input to the output, which is a bit confusing to say, but nothing's going to be flipped, nothing's going to be applied, and then it's just also going to be a 1 on the output. So the Zed gate will not affect it yet. So now if there's a 1 up here, so if we have a 1, input of 1 and 0, say, so here it's going to be, I'm actually going to be horrible at drawing this, I should have made my picture bigger, but if we have a 1 input to this line, then now that's the actual control that's going to be, like, it's going to be activated, and now we need to apply the Z function into our gate now. So nothing will happen to the top line because that's our control, but for the input, because it's 0, according to our function, it's going to stay as 0, so we just put it as 0 in there. Oh, that's not copy pasting right, so that's 0. Now, for our last output of the line, if we have a 1 input, it's going to have that Z function activate, but instead now, we are going to flip from a 1 to a -1. And that is how our CZ, like the truth table of our CZ, would essentially work. Sorry, I'll scroll that up so it's a little bit easier to see. Okay, so that's the truth table. So now let's actually work through the actual question and see how we would get an equivalent circuit gate there. So that's at least, I just did that kind of mostly for myself to be like, okay, I understand how this gate is working and why it's working. So now let's actually get to this. Obviously, you wouldn't have to show me what a CZ gate is on the midterm, but if it helps be clear, if you have time and it helps for clarity there, feel free to throw that out in there. Okay, so let's now actually draw the circuit diagram for this circuit, and I'm going to try my best to keep it as clean as possible. So this is Q0 on the bottom, and let's do Q1 here. And I'm just going to type it out just so you don't have to see me drawing in horrible lettering. And I'll zoom in here, hopefully it helps a little bit. So the H gates, we're going to have 2 Hadamards. Oh, sorry, that's not true. There's going to be a Hadamard on the bottom line, and then we're going to have a control gate, or a CZ gate, and then another Hadamard. So it's going to go something like this. Then I'll have a little H gate here. Then we're going to have our control gate, or our CZ gate. I'll make this I'll call this CZ, just to hopefully make it more clear, if I can actually write properly, just to make it more clear. And this on the bottom here is our control, top is our control, and bottom is our actual Z, is over here. Okay, so this is the circuit, and let's actually walk through the different parts of the circuit and then draw out what it would be in broadcat notation to work through it. So how I'm going to do that is I'm just going to start with our inputs. I like to split the circuit up. I'm going to call it A, and then the next part is going to be after the first Hadamard gate on the bottom, and I call that B. So this is the second part here. Then we're going to do after the CZ gate, which is going to be C, and then after our last Hadamard, and we're going to call that D. So now we can actually look at how both of the bits evolve in both parts of the gates. So the way I decided to do this is I was going to do all the different cases and then see how it evolves throughout the actual. Well, yeah, this is one way to do it. Not necessarily the fastest way, but let's do this way just as an illustrative example, because there's definitely different ways you could do it. So let's look at both of the qubits now. So the way I'm going to designate this is if it's something like our input here is 0 and then 0, so I'll actually do it like that, then what we can do is we can compose that into a 0, 0 because you can kind of multiply them in together, and then now we have 0, 0. So at A, because both of our inputs, that's if we say 0, 0, yeah, I'll call this the 0, 0 case. So a 0, 0 input case. Then at A, the inputs are going to be all 0, 0. Nothing's changed. There's no gates gone through it. So now at B, what we need to do is we need to apply the Hadamard gate to the bottom bit. So also just to be clear, this first bit is always going to be the top bit, and this second bit is always going to be the bottom bit. So just the same way he does that in class. So now what we're going to do, the way, and I'll actually write it out, is first bit is unchanged, but we're going to do H of a 0. And so does anyone remember how you apply a Hadamard to a 0, what that becomes?
0 plus 1.
Exactly. So then it's going to turn into 0 of 0 plus 1, because that's how a Hadamard gate works. If you want, I can rewrite that out, but hopefully that makes sense. So now what this is going to change our entire, like if we were to multiply in those two bit sequences and distribute them, this is going to become 0, 0 plus 0, 1. Because you times the 0 by the 0 and then the 0 by the 1, and you get this as our final output. So now this is at this section here, that little b. So now we've gone to the first Hadamard gate. Now we're going to want to go through the CZ. So now we have our input from our last section, which we will we'll do it in this, where they actually have the bits separated. We want to apply a CZ to our last thing only if the second one is 1, or only if the first bit is 1, only if Q0 is 1. So Q0 isn't 1 in this case, it's 0, so we don't need to apply the CZ yet, it's just the same. And so that's fine, so we can just say that CZ is the same as B, so we'll actually put B is equal to C, because nothing actually happens in this case scenario. And then at our D, the D point, we apply another Hadamard gate to the start, and that we should know that that's the identity function, but just to be clear, we'll work it out anyways. So 0 plus 1, and Hadamard. So if you remember, the way Hadamard works is it distributes into there, so we're going to apply 0, H to 0, and then H to 1, and then work out the math. So sorry, it's weird when I type it out, but hopefully it should make sense. We're going to do H of 0 plus H of 1. And let's work that out on the next line here. Sorry, I'll actually make this a little bit bigger, just so we can work with the math. So this is 0, and then H of 0, as we said before, is 0 plus 1. And then anyone remember what H of 1 is? 0 minus 1, perfect. So 0 minus 1. So that's that. And if we were to multiply it all out, we can multiply these all together times the 0, 1, and we can do, just to I just like to go back and forth between the factored and non-factored forms. It would be 0, 0, 0, 1, 0, 1, plus 0, 0. Actually, we can actually simplify a little bit earlier here, because this minus 1 gets rid of this 1. So we can take, since those cancel out, so now it's actually 0 of 2 times 0. And if remember from class 2, the 2 doesn't matter, so we can actually take that 2 out. So this just becomes 0, 0 right there. So that is our input case when it is 0, 0. Now this is going pretty slow at each of the cases. So if you wanted to, instead of doing this method where you check all the inputs at each of the 0, 0, actually no, scratch that. Don't, if you wanted to, you could reduce this entire step down to applying all the gates to both of the bits at the same time instead of separately. So the way I wrote that is you could apply, say if 0, 0 is your input bit, you know that over the, 0, 0 is your input bit, you know that over the entire gate, the way you're going to do is you're going to apply a Hadamard, and then a CZ, and then a Hadamard. So now since it's only affecting the bottom gate, the way we could actually write that is we could actually nest all these statements, and then do Hadamard, Z of Hadamard, and then this, and then apply it to our input bit, and that should be the exact same thing is working through all these cases. So that's going right from A to D. Does that make sense, what I'm doing there? Okay, hopefully it does, yeah, because if it doesn't, no worries.
But it will still like account for like phase kickback and stuff.
Yes, it absolutely will, because we have both of our bits like written here. So it's got the top bit and the bottom bit, so even if there is phase kickback, it'll account for that when we're applying all of our things, if that makes sense. Perfect. Oh wait, no. Sorry. That actually we only need to apply to the bottom bit, because we're actually dealing with the bottom bit. Yeah, I guess this wouldn't necessarily account for phase kickback if I'm doing it this way. So hold on, sorry, let me think about this, because the way I did it might not have factored in phase kickback between both. Yeah, definitely this way did. So if there was any phase kickback, you would see it, and it didn't. But I'm trying to think of if we did it, if I did just the bottom bit. So the way I did it, I just did the bottom bit and assumed the top bit didn't change, but that's not exactly a good assumption. So I think we should keep doing it with this way and go forward. Because yeah, maybe we could do it with the 0, 0 actually here, and it work out the exact same as there. Pretty sure that should work out if we keep going it like this. But we have to be clever and make sure that we apply the H. It's going to look not like this, but it's going to look like H of Z of H of the first bit. Of this. So H applied to Z applied to H of the first bit, because the actual application is only happening to the second bit, not the first bit, if that makes sense. Hopefully it does, but if not, we'll just keep going with the other way. You guys prefer I go with the other way or try this like more compact form? Doesn't really matter to me, but
I think the first thing.
yeah, let's go with the first way. Yeah, this is just to save space if you want to. So we did the 0, 0 case, and sorry, I know we're running out of time, so I'll try and do this quickly. Let's do the 0, 1 input case. This actually be in bracket notation. Put that there. So A, nothing's going to change. So we're just going to put our inputs as 0, 1. So A is equal to 0, 1. Then once it goes to the Hadamard, we need to actually apply the Hadamard. So it's 0 is the first bit, then H of 1. And then we should know that that's 0 times H of 1 is 0 minus 1. Minus 1. So that is the input there. And we can expand an output if we want to. So that's 0, 0 minus 0, 1 there. Then at C is also going to be the exact same as B, because the first bit is still 0 no matter what. So this first bit here is 0, so this Z is not activated, so we can just say that it's the same thing there. And then our D case, we're going to apply the Hadamard at the bottom again. And I'm going to skip a step here and just simplify, because we know Hadamard applied to Hadamard is going to be the same thing. It's the identity, so we can say that it's 0 and then 1. So sorry, H of this. So we're applying H to the second bit. So yeah, the tricky thing is making sure you apply to each of the bits and not to both of the bits, and like keeping your everything consistent. So I'm skipping a couple steps, but if you believe me and remember this identity, it comes out to 0, 1 or 0, 1 there.
Could I ask a question about how like factoring works in the context of this?
Sure.
Because I'm confused, because the professor will always say like the first bit will be multiplied by the second bit, right?
Mm-hmm.
And then when you like apply all the algebra and stuff, and you get like a long equation, and you factor out something, whatever you factored as the first factor will be the top bit, and then the second will be the second bit.
Yes.
But can't you factor out like different things, and then you would get different values for like the first bit?
So you could factor out. I think I get your question is like, if you rearranged it, couldn't you factor out like maybe I'm trying to think of like a scenario. If you factor out a different way, it should be different bits essentially. So as long as you have a 0 on, like each of the bit is composed of a 0 and a 1, or just a 0 or just a 1, like do it in the way, like the superposition form, it will always come out that it should be the first bit is on the left side, the first bit on the second side. Now, that's a little tricky, like, because you're saying, because, like, what if you, like, because of distributivity, you could flop or, like, multiply the factors and you can rearrange the factors. The key is to always make sure that everything is in, like, keep it in sequence as possible so we don't lose our sequence. So it's a bit arbitrary, like, the way he says it, that, like, you need to make sure that everything is like the first one is the first bit and the second bit. As long as you keep that order of the order of those bits when you like factor and expand and everything like that, then that's okay when we factor, as long as everything is in the same order, if that makes sense.
So it doesn't matter if you can figure out something to factor, it will always just work out. Like, because I'm confused if like you factor out something different, like you have a long term and then you choose to factor something else, like just part of what, it could, like.
Isn't there only? Sorry, go ahead with your question. Sorry.
Like I have an example, but I can just ask you after.
No, show me the example if you want to, because this is an important question.
Okay, so like he had in lecture like, I don't know how to, let me go check.
Yeah, sure, that works. Get this out of the way.
He had this in lecture, right?
Right.
So he had, let me turn my brightness.
Yeah, okay.
So like this is the term, and then that's how it's like factored, right?
Right.
So what if you took this term and you factored out this term first, and then you had this left on the other side? That wouldn't work. Is that what you're saying?
Do you mind if I write this down on paper? Because I've actually factored it. So he started with this right-hand side or the left-hand side?
He started like this, but like I'm assuming you can factor this back into that, so it doesn't really matter, right?
Yeah, it should. Let me actually write that down so that we can do the question. Sorry, mind if I just do that there? And yeah, I know, sorry, we're kind of short on time, but these are all great questions, so I do appreciate them. So here is our like factored version, and here is our actual like written out expanded / we'll call it distributed because that's what it's called. This is the distributed version plus 1, 0. So you're thinking that there's another way that we could factor this to not get to this?
Yeah, so like that second term, like I think I'm getting it, but that second term, like the 0 minus 1, like on the left-hand side.
This one right here?
On the left-hand side.
Oh, sorry, 0 minus 1?
Yeah, so that, I'm assuming, like I was thinking like maybe we could factor it out of the right-hand side and it would show up as the first factor on the left-hand side.
Right.
But I guess that wouldn't be possible because then that would require like rearranging the terms.
Yeah, I'm assuming that like at least the way I have been working through it is like make sure you don't rearrange the terms as much as possible, unless like I don't think that's a good question actually for Dr. Sabri because he might like just get the math a little bit more. But I'm pretty sure if you keep everything consistent, like when you obviously do the FOIL, it's 0 times 0, then 0 times 1, and then -1 times 0, and -1 times 0. Like do the FOIL inward outward the way it's kind of shown, it should hopefully be consistent. But that's a great question because let me make sure that that's the case though. Let's take this and make sure that we can't factor it any other way. Let me scroll up so that actually you have a little space there to see. So here when we factor it, we want to make sure that there's a 0 from the left-hand side and then a 0 or 1 coming out there. So I think, let me just write this down because easier for me to write than to type. And sorry, I know we're going a little bit over on the time, so I hope you guys don't mind or don't have anywhere to go. So I think there should be only one way to factor that to get that equation. Let me make sure though. So 0 plus 1. So if we get a 0 there, and then I think that is the only way to factor, but you've got to make sure that these are in the right order when you actually do it. 0 minus 1. That should be 0, 0. 0 minus 1. Yeah.
Yeah, I think you've convinced me. Like,
I hope I've convinced you. I'm making sure that I convince myself and that it's not, I'm not telling you the wrong thing. But I'm pretty sure if you FOIL in that order, it should always work out. I think that the only way to actually get it is this, as long as you keep these in order. I'm not good at going from left-hand side to right-hand side on this bottom one, but I'm pretty sure that is the way. So this will be the first top bit, and this will be the second bit. If that makes sense.
Okay.
Yeah.
So I just have to keep them, the terms in the order there, and then it should be good.
Yes. Yes. Definitely keep the terms in order. And then, if it doesn't make sense, like for some reason, well, it's hard because it's quantum mechanics, so it should make sense. But double check, make sure throughout that it does make sense. So sorry, for the rest of this question then, basically keep going through the different input cases, and then at the end you can see the same way we saw with the question number 2, that if you flip one of the bits, it will be a particular single gate that it'll go through. So I'll leave that as an exercise. But I'll give away the answer since I will be releasing the answer anyways. The actual, if you look through and then like say put it in a truth table, For this one, if you just did, where's my actual notes on it? I'm pretty sure it's just a CX between, this is notes 1, sorry.
There's only 2 bits. CX between.
Q0 and Q1, right. Yeah, you're right, Q0 and Q1. Yeah, glad that you came to that same conclusion. But that is the answer. Okay, thank you for listening and for staying an extra 5 minutes. I really appreciate this, guys. I know this is a bit of a longer tutorial since going through, but if anyone has any other questions, please let me know. We'll work on that answer key and try and get that out. So hopefully more, you can work in practice for the midterm.
I just I couldn't do 5.
Yeah, 5 is a tricky one, so I'll work with Dr. Sabri to make it a good explanation of 5. I should have started with that one, but that might have taken me, well, not the entire tutorial, because it's not going to take that long to do a midterm, but yes, we'll get those out there. All right? Okay, well, thanks, guys. Really